Welcome to Planet Geo, the podcast where we talk about our amazing planet, how it works, and why it matters to you. I view us kind of having a machete and hacking our way through the weeds here. And, you know, we know really broadly where we're going, but not exactly. And all the listeners are behind us being like, okay, these guys know mostly where they're going, but maybe not exactly.
Well, I hope we're in the throes of this series on Long Valley Caldera, but we're using the Long Valley Caldera once again as a way to explain broader geologic concepts.
Yeah.
So that's our starting point, and then we're going to use it though to teach geoscience.
And this is something you really nicely came up with. We were talking, you know, our last episode was all about kind of the high-level summary of Long Valley Caldera, why it's complicated, why this was a much bigger bite than we were really thinking about it was. And then you framed it this way as like, well, what if we took all these little pieces that we've learned about Long Valley and really kind of step back and taught them from a basic level, things you would learn about in the introductory, actually second-year undergrad. We're going to touch on stuff that's like second or third-year undergrad geoscience education. So we're going to get into the weeds for sure, and we have to, but we're still simplifying it down. Like this is an utterly complicated area. The Western United States tectonically is very complicated. So we're still simplifying in some way.
I think about it this way. There are so many papers that have been written about Long Valley Caldera, and it's unbelievably complicated and convoluted. And so you said that we're kind of whacking away with a machete, as we're making our way through the weeds, but it may not seem that way as we go through this because we've done the job of simplifying this down. So if you are one of those people that are listening to this that have done research on Long Valley Caldera, you might think, well, they're not in the weeds,
Yeah, they're just really dumbing it down. Yeah, right. I see where you're going. Yeah, totally. Yeah, if you're listening to this and you're an expert in the Western United States tectonic evolution, this is not, we're gonna skip over some parts because we kind of have to keep it understandable and tractable in a half an hour discussion. And I think that's valuable, right? Like that's the point here. We're going to talk about, Chris, this episode is really why here is kind of the question. When it comes to Long Valley, the question is why here? This is a weird place for a very large volcanic eruption and a whole bunch of volcanic eruptions to have occurred. At least in your intro level geoscience 1, first year undergrad sort of mindset, it's a weird place. It's not typical. What we're going to talk about today is where volcanoes form generally, which, I mean, that's kind of our intro thing here. And then we're going to lead into why is Long Valley where it is today, because there's really good geological reasons for it. It just might take us a little bit to build to that point. So, Chris, when you are teaching, advanced placement geology, college level geology to high schoolers who have 0% background knowledge, how do you talk about, I know you love volcanoes, like you really love talking about volcanoes. How do you lead into this question? Why do volcanoes form where they do? What's your summary or overview of this for them?
My students will come at it with some background information because I don't do volcanoes until later on.
Oh, okay. So you've covered plate tectonics, all that?
Covered plate tectonics at that point. And so you cover some of the basics of plate tectonics, like, the addition of volatiles to super hot rock and what that can do, which is at play here at Long Valley Caldera. And so they have some of the basics. And then I start off by saying where from a geoscience perspective is magma going to be generated on Earth? And so we just kind of bullet list or brainstorm the conditions that can cause melting, which is kind of where we're at right here today.
Yeah. So I think if you just asked that question to anybody and said, where does magma form? A lot of people will turn to subduction zones. They'll think of Japan. They'll think of the Sierra Nevadas, the Cascades. They'll think, oh, wait, okay, these are the Andes, right? They'll think of places where there's a big volcanic island chain. We hear about Mount St. Helens. We hear about these big volcanoes, and they'll think of that. And that's a very dominant one on Earth. It's not necessarily the biggest, but it is a very major way. And the way that occurs in the modern Earth, in the very modern Earth today, is that an oceanic plate is diving down beneath the continental plate in a subduction zone or diving down beneath the younger oceanic plate. And that downgoing plate is bringing water. It's bringing carbon dioxide in mineral form, kind of like a sponge. You described it as a sponge. It's bringing that water down into the mantle. It gets heated up. It gets compressed. and that water and that carbon dioxide gets driven off of the slab. That water then makes its way into the mantle, and what you refer to as adding volatiles, flux melting is really what's going on here. Adding water to hot rock deep makes it melt. It drops the melting point. It's like dumping salt onto ice. It drops the melting point drastically. So at the same pressure and temperature conditions, you can melt the thing because you've flux melted this thing with water and carbon dioxide and things like that.
That's right. And, so when I talk about this to freshman level, so young beginning geoscience students, we don't get into any of that. We kind of lie to them, or at least I do at that point, and I just say,
well, you have to take the intro level.
You do, but it's okay. It's okay, and you say, well, subduction happens, and they know that it gets hotter with depth, and so then you just say that this plate will begin to melt, and that magma then is less dense than the rock that it came from, and it begins to ascend and rise up towards the surface. It isn't until they get into geoscience, my class, and the class that you teach, the equivalent of that, where that now you can talk about, because they're ready for that. They know a little bit more chemistry, and you can dive into the weeds a little bit more and say, well, let's just tweak what we said. It's not really the melting of that plate. It's actually the wringing out of those volatiles that rise up into super hot rock, but it is rock. And the addition of those volatiles, like you said, adding salt to ice stimulates melting. In this kind of your doctory way of saying flux melting. I never refer to it that way. But.
Well, so I always, Chris, when I lead into this stuff, I always I say, okay, there's 3 ways to melt rock on Earth broadly. And I mean, really simple versions. And I asked them, how would you think, ask this class of 200, 250 students, how do you melt rock, do you think? And, inevitably pretty quickly hands shoot up and they say, oh, just heat it up, which great. That's definitely one way to melt rock, heat it up, right? Then I say, okay, what are some other ways? And then the room's pretty quiet for a while. They're like, wait, hold on. There are other ways to melt stuff? And then you have to bring in these other analogies. And the salt on ice is one that, you kind of have to tell them, are you actually heating up the ice in your driveway when you dump salt on it? And the answer is no. You're just adding something else to the recipe, which changes the melting point. And so that one brings in the volatiles. So I think that's always a good analogy. The last one, the third way we melt rocks on Earth, which is the one that is relevant for Long Valley Caldera, I find students take quite a long time to get to. And the analogy I use, Chris, and I'm not sure how good it is for applicability, but is boiling water at high altitude. When you cook,
that's good actually. I like that.
Is it a good one? Like you cook.
It absolutely is.
When you're up in the Tetons, camping with your family and you're trying to boil water to cook stuff, the water boils at a lower temperature. So you have to cook for longer, right? Like if you're cooking pasta, you got to cook it for longer because it's boiling at a lower temperature. And the same thing happens when you have rock turning into liquid. Instead of liquid to vapor, it's doing solid to liquid. And we call that decompression. So if you take, and we'll talk about this later, but if you take a rock under pressure and you release the pressure, you can induce melting sometimes in certain instances. And we call that decompression melting. That's the third way.
I talk about this in the context of the core of the Earth. We have a liquid outer core and we have a solid inner core. And they know that basically there's this geothermal gradient where the temperature gets hotter with depth. So they know that the solid inner core, it has to be the hottest part, the hottest layer of the Earth, but yet it's solid. So why is the liquid outer core liquid when it's not as hot, when it's compositionally very similar to each other, right? And it's just because pressure makes it that way. Pressure is so immense that it overrides the effect of heat. Pressure becomes the more important variable in that kind of heat pressure recipe for whether something's solid or liquid. So
I like that. That's a good analogy. And so, Chris, on Earth, where does most of our decompression melting? Decompression melting is a major, probably the dominant melting mechanism on Earth. Where does it occur mostly? And I think this is an obvious one that people don't usually come to this conclusion right away.
Oh, you don't think so?
I don't think they get. Right. I mean, it takes a while to think about it. To think, okay, where is decompression melting happening? You got to go a couple steps deep into geoscience knowledge.
Okay. Most of this is going to happen where you have spreading centers. So the mid-ocean ridges, you have this decompression melting where you have this really hot, soft, kind of plasticky, it's this asthenosphere layer that is rising up convectively. And as it does this, it's not really solid rock. It's not really liquid. It's got properties of both. It's like right at that melting point. the heat and the pressure is just right to create this kind of soft plasticky material. As it rises up, it's going to decompress and it's going to like partially melt. It's not going to melt, but it's going to stimulate partial melting. So you'll take this ultramafic material from the mantle that's rising up, and we're going to partially melt that, but we're going to melt any of those, the lower temperature minerals are going to come out. And so you're going to, instead of ultramafic, you're going to get then this kind of distillation process, a mafic material that comes out, and the result is usually basalt.
Yeah, I mean that's how we form oceanic crust on Earth is decompression, melting, spreading centers, the mantles upwelling. Perfect. So, Chris, maybe we should move into why here, why Long Valley. And we talked about decompression. This is the mechanism, but in order to get decompression, we need stuff rising up to the surface. And there's a couple ways tectonically you can do that, but I think this one, Chris, this is like a structural geology kind of 101 type of thing. A process called transtension, and we'll turn to the first image here. And this is where we're moving from the intro level understanding of faults into something a little bit more complicated. This is classic geology. Like, there's always rules of thumb in geology, but never rules in geology, because it gets complicated the closer you look at it. So if we imagine a fault, I mean, we talk about 3 different types of faults, right? At the intro level: normal fault, reverse fault, and then strike slip, like San Andreas, where it's just 2 plates sliding past each other. Do you get into transtension and transpression?
Yeah, I do. Not with my youngest students, but with my juniors and seniors, and
Sure.
These are mostly college-bound students, and they're taking this for college credit. So, yeah, I do with that, because you alluded to the San Andreas Fault. In a idealized class, you talk about transform faults, where one plate is just kind of neatly sliding past another plate, moving in opposite directions or in the same direction, just at different rates. But you don't always get that. That's not what usually or always happens in geoscience. So the San Andreas Fault, it's got this S bend in the San Andreas Fault in the southern part of this. Well, that S bend is going to create compression due to the relative motions of those plates. But in the case of Long Valley here, and you look at this image number 1 here, this is a great GIF that you created, where the relative motions of the plates, there's a bend in it, this S-shaped bend, but it causes where that bend is, the plates to actually pull apart. So instead of a typical transform boundary where they're moving past each other, at that bend, they're actually moving away. That divergence causes decompression.
And Chris, I think this is really useful for people to understand, because you rarely get a perfectly linear transform fault that goes the entire length. Like, there are always little bends and kinks and promontories. The plate, there's different strengths of the different plates. Like, some parts stick, some parts slip. Old faults
different
can get reactivated, right? Yeah, there's all sorts of complexity here. So there's always little kinks and bends and promontories. And as soon as you have that, as soon as you have a kink and things are sliding past each other and you kink it, you're either going to get compression, as you said, or extension, in this case, the Long Valley. So you'll see a lot of, if you look into the literature about Long Valley, you'll often hear the term transtension, transpression.
I like that. Transtension is such a great way, because it's a transform and it's tensional stress at the same time.
And you got to think about we're talking about tectonic plate movement. The scale of the transform is huge. The plates are sliding past each other. But the more we zoom in, and the more complicated. That's a really rough boundary, right? There's not going to be a perfectly straight knife edge line cutting across tectonic plates. We zoom in, gets complicated. It's rocky, it's rumbly. There's structure to that boundary, and tension and transpression are a natural outcome of that.
I have a question for you. So do you find it that some of your students don't readily understand what you mean when you say tensional stress?
Yeah. Oh, for sure.
Yeah. Mine don't. So I always talk about, I'll grab a rope and I'll say, okay, I'll give one end of the rope to a student. I'm standing in the front of the class, and I'll say, all right, we'll put tension on the rope.
Yeah.
And they know what to do. They'll straighten it out. They'll put more tension on the rope. Okay. That's tensional stress in geoscience. We're actively pulling it apart. So
interesting. I use extension. I say, okay, extension. Okay, what's part of that word? Tension is part of extension, yes. Right? So, and then add trans to it, and it's tension that's occurring along a transform fault, again, because of this rough edge to the tectonic plate. So that's that's a very, very simplistic way to look at the Long Valley Caldera. This next image, Chris, should we like talk about the regional tectonics here just a little bit?
Absolutely.
This next image, okay, this is this is complicated. We made this, we want to work through. There's a couple of main takeaways from this image. The first takeaway is that there's a lot of complicated tectonics going in the western United States here. That's like the first high level thing. And then we're going to zoom in a little bit more and talk about, at a simplistic level, why the Long Valley Caldera is here in particular. Why is it right where it is? This image.
Well, let's break this down. Yeah, let's talk about the basin and range, and let's go into the MENA, transition, and let's do this.
You got to imagine this image. We're kind of zooming in on the western United States, the western half of the United States, from the Rocky Mountain front out to the Pacific coast. And if you kind of work from westward all the way east, if you're kind of going from the coast, get in a plane in LAX and you're flying east, you start out on the Pacific plate and the San Andreas fault is right underneath you. So the Pacific plate is moving up and to the west, and the North American plate is kind of moving relative down into the east a little bit. So there's the San Andreas fault. We all kind of know that. San Andreas fault, you move in, you get over the Great Valley and the Sierra Nevada block. The Sierra Nevada is this huge block of this. You ever gone to Yosemite or you go up into the Sierra Nevadas, it's all granite, right? This is all granite. It's this huge mountain range block that's uplifted in pretty high elevation. Then you get on the eastern side, you keep going east, you get on the eastern side of the Sierra Nevadas, and you start to get eventually into the Basin and range. All of a sudden you're in Nevada, where you're driving across. I mean, we've driven through this part of the world, and you have mountains on one side, mountains on the other side, and you're in a big, long valley. And you end up in that what's called the Basin and Range province, basins and ranges that are on either side of you, and that goes for a long time until you get inboard to the Colorado Plateau and you get into Arizona, and etc. So that's where we kind of work. San Andreas Fault, Sierra Nevada block. Then there's this little belt that we'll talk about where Long Valley is on the eastern side of the Sierra Nevadas, and then you get into Basin and Range extension. Basin and Range
I think
province.
The takeaway with all that, Jesse, is you have this really complicated intersection of a lot of tectonics going on and a lot of faults, and that plays a role in the culmination of this magma that accumulated here. Okay, there's so many faults, and there's so many different faults that are at play.
So, Chris, let's break this down here. We're going to focus first Sierra Nevada block. These are all 100 million, 90 million year old granites. This huge batholith, Sierra Nevada batholith. They behave, as you could imagine, as a big block, tectonically a big block. That's a big piece of crust that's pretty hard to deform. It's sitting there. We're going to think of it as this big block that's just sitting there, and everything's moving around it. What's the next most important thing, do you think, out of this?
Well, first of all, Jesse, I was struck with something. You and I don't think have ever been to the Sierra Nevadas together, have we?
No, that's true. Not together. Yeah, I know. We got to rectify that. I mean,
that is a problem.
It feels like a big problem. Yeah.
It doesn't happen very often where we can say that, I feel like.
I know.
We've been a lot of places together, but yeah. So, all right, the next big block is this basin and range that you talked about. This is straight up. This isn't transtensional. This is tensional. This is extension of a massive part of the western U.S. In fact, like this is, to me, it's shocking. If you think about a bar of taffy, and you put tension on you put your hands on both sides of it and you put it under tension, the result is it's going to thin in the middle. And that's exactly what happens during this in the basin and range due to this tension is this thinning. And it's 2 times really thinner. Yeah. So it's half as thick as what it was before this started.
It's an amazing amount. If you go and reconstruct all the faults of the basin and range, it used to be twice as thick or twice as wide, half as wide, twice as thick. And now it's twice as wide, half as thick.
But it's still,
it's amazing.
It's complicated though, because when you think about it's not just thinning, because you still have you have ranges and basins, some parts of it are sinking and some parts of it are going up relative to that. It's complicated, but yes, overall, half as thick as what it was before it started.
So, okay, we've got those two features as kind of a setup, and there's a lot of debate. I mean, go back to our Basil Teagoff interview talking about different models for forming the Rocky Mountains. There's a substantial amount of debate about how these things kind of relate to each other, when they started to occur, what the tectonics was, etc. But we're going to say Sierra Nevadas, that's a big block, basin and range, separate kind of thing. Those are a little bit cleaner to understand, and in between them it gets really complicated. And Chris, here's something that was quite interesting that I did not know until we started diving into the literature about the Long Valley Caldera here. is that the San Andreas Fault is obviously, it's there because there's stress. The Pacific Plate is sliding past the North American Plate. Obviously, there's stress that is there. I did not know this. The San Andreas takes up only like 3/4 of the stress involved. So 75 to 80% of the stress is accommodated on the San Andreas. The other amount is accommodated on the eastern side of the Sierra Nevadas, what we have in this image called the Walker Lake Belt in the eastern California shear zone, these purple areas that are just on the eastern side of the Sierra Nevadas. So the Sierra Nevadas are kind of caught up in between two big deformation zones. The San Andreas is the one we all hear about, but then there's this other one that is still a lot of movement going on the eastern side of the Sierra Nevadas.
That's right.
That's super interesting to me. I don't know. What do you think about? I mean,
well, I agree. You know, the Mina deflection, the Walker Lane, Eastern California shear zone, that's a lot to say. Those are the technical names for it. But what's the takeaway with this? And the takeaway is that Long Valley Caldera is this kind of kink. It's this weird intersection of those. And that's why Long Valley Caldera and, well, you know, we haven't actually said this in this episode yet anyway, is that this was the third largest volcanic eruption in modern geologic times. Yellowstone has the top two, then Long Valley takes 3, and then the other Yellowstone eruption takes 4th place in modern times anyway.
Yeah.
So
the fact that the San Andreas is not the end of the story. This big fault that we all know about, it's not the only thing. It's not the only game in town. There's this Walker Lane belt on the other side of the Sierra Nevadas that is doing this sort of same motion, accommodating some of this strain between the two tectonic plates sliding past each other. Which brings us, Chris, at the end, you mentioned it, the Mina deflection. The Mina deflection is the kink. Well, there's a little bit of debate about this, but it is part of the kink. And the Long Valley Caldera, which we've highlighted here with a star, sits right on the eastern side of the Sierra Nevadas, right in this deformation zone, but there's a kink in the deformation zone. And as we talked about before, we can get this trans tension anytime we have kinks in transform fault movement. And we're sitting right in a kink. You can kind of see it. The Sierra Nevadas kind of hangs a left as you're going up. It goes kind of north, and then it goes northwest. And that creates kind of a gap where we can get this trans tension going on. So I don't know. This is complicated. We've simplified it down a lot here, but I think does it convey the point, Chris, here a little bit, that this is how we get tension and extension in an area like this?
Well, I hope so. I think it does. But then what's the other takeaway with that, Jesse, is that what kind of faulting do you get with tension?
Oh, perfect. So I just want to note that I flipped forward here to image number, this third image that we're going to talk about. And we're zooming in on the Long Valley Caldera, which is outlined here, but we're just a topo map shows the White Mountains on the right side, Sierra Nevadas on the left side or the west side. We're outlining the caldera, Long Valley Caldera here, and then all we're showing is major faults, and these are all normal faults. So they're all normal faults, extension faults. The Mina deflection is just off this image to the north, so that big deflection bend we're seeing is just off to the north. It's not on this image, but
you know, just to back up a second and talk about what does the faulting mean? Well, if you have compression, then you're going to get what we call reverse faulting and thrust faulting. It's easy to think about mountain formation when you think about compression. You're thickening the crust and you're getting these slivers of rock that are jammed up over top, like kind of an echelon. And you get these big thrust faults and reverse faults where the hanging wall of the fault moves up relative to the footwall. This is the opposite. So these are mountains that form from tension instead, and they can be spectacular.
Oh my God,
some of my favorite mountains in the world are extensional normal fault results, such as the Tetons, right? And all of the Basin and Range and all of the Long Valley Caldera, because that's what makes this place unique is you have trans tension. You also have the Basin and Range, which is straight up tensional. And so it's normal faulting everywhere you look.
Everywhere you look, and you can kind of see these big normal faults have been mapped, both interestingly, on the edges between the valley and the mountains, as you would expect. I'm going to skip ahead, Chris, to the next image here, which is a GIF we made talking about Horsts and Grabens, and this is kind of very normal. Basin and Range is kind of the the textbook example of this kind of thing. You create tension, you pull the crust apart, you have blocks that drop down and fill in that space, and then blocks that are kind of thrust up into that space as well. They're rarely thrust up, but if they're rotating a little bit, they can be going up a lot. But you get this kind of up and down action forming a valley, which is the graben, and then the horst is the up thrust mountain belts on either side. And one thing to note, if I just go back to this image about the normal faults, obviously there's normal faults on the edges of the mountains, like where the mountains are going up or in the valleys dropping down. But there's a lot of normal faults in the valley too, and those are a little bit harder because they get covered up with sediment. The sediment coming from the mountains dumps into the valley and kind of overprints some of the structure. So this is what we have. This is the setup. Is we have this broad regional extension. We have this horst and graben type of thing, and Long Valley Caldera is sitting in here.
And extension leads generally to two things, right? Extension can lead to uplift, the horst part of it, and the melting of the mantle. So the mantle's, this thinning of the crust is bringing that hot mantle closer to the surface, as we already said, and but it's worth saying again that the other thing that it leads to is normal faulting, and then this kind of horst and graben. And these are, I think, Jesse, German terms, right? Horst means to hoist, and graben means grave or sunken.
Okay, I didn't know the origin of those, but actually, that's interesting. Yeah, so in this horst and graben, GIF that we're looking at on the west side of the horst is the White Mountains. If we're looking at Long Valley Caldera, the east side, horst on the east side is the White Mountains. The horst on the west side will be the Sierra Nevadas, and Long Valley will be in the middle, between them.
And that Owens Valley, the main part leading into Long Valley Caldera, that's the graben part.
Yeah, in the south,
in between
down here,
the two blocks. Yep,
yeah,
that's right.
Yeah, exactly. Yep. And you'll see normal faults on both sides of these things. And again, I like this third image here. Go back to that because it kind of shows us how this horst and graben feature is kind of extending. We're kind of in the kink, and we're getting a broader. The normal faults are kind of, they're parallel down south, running mostly north-south in the north-south orientation. And then as we get up towards the north, right around Long Valley, the ones on the left side kind of hang up and go to the northwest. And it's kind of showing this extensional environment, both with the normal faults and the normal faulting is kind of wying out, and it's getting broader and bigger because of this trans tension. So I think that gets us to the point, like the tectonics here are very complicated. I think we've highlighted that without going into too much in the weeds here, right? Like, I don't know, how do you feel?
I think so. So let's kind of summarize this up, where Long Valley Caldera is created because you have this unique intersection of faulting. It's very complicated, but there's a kink here which caused the accumulation of magma. But we led off by talking about where do volcanoes form, or in other words, Jesse, where does magma form from a geoscience perspective? Right. And it forms at subduction zones. It forms anywhere you have decompression, such as mid-ocean ridges, spreading centers, or extension beneath continental crust. If you cause enough thinning, then you can generate this partial melting of the mantle below. The other thing is, too, Jesse, that I think that this happens a fair amount, is people confuse Long Valley Caldera with a hotspot.
Yeah,
But that is another area where magma is generated. And we've talked about this before in our CampGeo visual podcast book, if you will, on the basics
we've talked about
of
it, Yellowstone. And actually, Chris, a lot of some of the discussion we'll have here is juxtaposing the Long Valley Caldera against Yellowstone, because there are some similarities to them, hydrothermal features, shallow, big eruptions, but there's some very key differences as well, and that, I think, hopefully will become apparent as we work through various episodes talking about the basic intro-level geoscience concepts in the context of explaining the Long Valley Caldera geology as well, and the lead up to this ultimately very, very large eruption that occurred. So
that's right. We're not there yet. About what happened after that, what happened next. This story wasn't over.
So we're not there. We're not actually even close to being at the big eruption event. The next episode we're going to talk about is the lead up. There's a whole bunch of basaltic volcanism which helps us tell this geological story. And so we're a couple episodes away from talking about the big one still. But there's so much interesting stuff to cover. It's just a totally cool place.
Absolutely.
All right. Hey,
All right.
if you want the images of this, you can follow us on YouTube or download our CampGeo mobile app where we have visual podcast series. These episodes will be posted there with the images that you can listen and learn along the way. Send us an email, plangeocast@gmail.com. Follow us on all the social medias @plangeocast.
Cheers.
Peace.